Yeah, it's fine.
Okay, good morning. We're going to start the session. Our first speaker, we have moved the program a little bit because Francisco is surrounding data. So the real talk will be at the end of the session. Our first speaker is Vittoria Zanchettin. Please welcome. Okay. Okay. Thank you. Okay. Good morning, everybody. I'm Vittoria Zanchettin. I'm a postdoc at the Innovative Observatory of Zanchettin, Vittoria, Italy. And today I will present you the work about the Zihuagn duality candidates at Sub-Arcsecond. This work is carried out in Zanchettin and non-poly thanks to several collaborators that you can see here, and also many others. This is not a real talk, so this is the work. I'm trying to go a bit slower during the introduction. So, why dual are interesting and important? Well, dual are the population of massive supermassive black hole, and therefore the progenitors of the emitters of frequency gravitational waves. Additionally, they are very important to test model prediction of supermassive black hole and galaxies coevolutions, since they are a final state of galaxies. And what should we study these systems? Well, first of all, to test these models for galaxy black hole conformation and coevolution, to understand the physics of the convergence and the agent fueling after mergers, and to predict and interpret gravitational wave signals. Okay, let's go to the gravitational waves. Okay, this is a very important book for gravitational waves. In particular, when I talk about supermassive black hole, what is important is the gravitational waves emitted at low frequencies. In this region, we have the PTA, which is here. This is the redshift versus the black hole mass. And PTA will be sensitive to spiral black hole of significant data and masses. Instead, future result, will detect matters from the ball in a lower range, but compared to PTA, we will be able to detect the stimulants. So what is the okay? This is a plot about the evolution rate, so the distance in function of the time. As a function of the separation between the two supermassive black holes. So here we have the dual, so we have different processes that can help the two black holes to inspire and merge. So we have the first slide, we have the frictions and happening, we have the stars and gas, and then only when the two black holes are very close, so we talking about super scales. This system can be gravitational waves on low frequency. So this is a very long process. So we should take some significant data years. Therefore, we expect to have a minimum of systems in the same post-merger of galaxy, and therefore to have a widespread population of dual and scales. So now we talk about the supermassive black hole. Dual supermassive black hole which both operate galaxies, so shown as a here. And to be clear, we can distinguish between dual gen and binary gen. Dual gen are the ones separated up to 100 kiloparsec, and the initial KG depending on the words or the work, but the important part is that again are not gravitational bound. Instead, when we talk about binary region, so the closed systems at up to 10 parsec or parsec scales, we talk about systems which are gravitational. But this presentation is about Gaia. So, about the importance, okay. What we can do with this Zihuagn? Well, we can test galaxy supermassive evolution model and understand the vector merging, or try to understand energy free after models. To do so, we have to derive important quantities and to compare models. Like we can derive the differential solution, the supermassive vector mass function iteration, the density, vibration, and so on. This is an example from two observations, the aspect one and the horizon about the equal mass distribution and the separation distribution in a functional distance. And of course, we want to predict and help in interpreting gravitational signals. So these are very never tested predictions that are very important. So, how do we take as observation? Well, at the local universe, we have few detector systems, but it's not really also to classify them. For me, I actually is above 0.5. Okay, it's not really high, not really the galaxy up to, okay, above that. But, okay, I'm interested in the pressure range, so something that was important. And we work also systems in the same house galaxy, okay? So after matters, model predicts the separation up to 700 parsecs for systems in the same house, so this is our threshold. And you can see this apart from 7,002. This is the region of this separation versus ratio, and this is the region which we are interested. So, which is important? Well, as I can say, we need closed systems. That means that in the ratio range, we need systems separated up to 0.8%, which means that we need high resolution. Additionally, these systems are rare compared to single systems, so we also need a large scale population. So how can we detect the systems? First of all, we have to select candidates. So we need to select quasars in this ratio range with close components. Okay. Second, we should study the attention. These are the candidates, but these candidates can be three main things. Okay, can be dualism, can be dense systems, so we can see the image of the same agent, application, and so on. And or it can be just the transline of the GM or so you can start see. And once classified, we study measure the physical properties and do a comparison of what's talking about. So, how to stand comparison? This is this is not all the methods, and these are the methods that we use in our channel to select systems. The first one, and the one that we'll talk about, is the Gaia method presented in Municipal 2022. The second advantage of the Gaia survey, these surveys will keep you up to a magnitude of 20.5, that means volumetric luminosity above 45.5%, which means that we are targeting luminosity diameter 1 luminosity. And with a separation between 0.15% and 0.7%. This is an ongoing project which is presented in MEGARA 2025 using UP to select candidates. The advantage here is that we are looking to less luminous systems, but that is more difficult to classify them because, of course, they are less luminous, so there's more time to compare. So, how Gaia? Well, Gaia is doing several studies of the sky. We have the 1D and profile, and what you can see, we can search like AGN with 2 peaks in the light profile above 10% of the cases. This is a keyword you can find this kind of system. So we have scanning surface systems. And this method we were able to detect multiple systems. So we are sure that there is multiple system, but the point is that then we need to classify them. First of all, what we do? First of all, we want the total spectra of the systems. Why? Okay, because we want the redshift, want to be sure that it is the primary therapy AGM, and also we want to discard the presence of them. So we have a lot of data. We use both our data from SDF and data, and then we have data from entity, GMG, not forced other spectra. What we do? From this spectra, these are two examples. We measure the redshift. We see problems, so we are sure that the primary is abundant. And then PhD or group, because we might consider the machine learning code to try to fit is find if there are certain features to try to avoid to observe later objects which are AGM. In this way, we are able to reject the sum of the system from. So after that, we have to go with the high. So we need high resolution. We need to resolve the two systems. To be sure, we have a lot of data both in optical and very different. I will show one example for data. These are the data from the news. We have a large program with the news model led by Ching Chen group, and we are looking for the dual candidates. Here we have an example. In this case, you see the green orange is a star, means the species is way 2 again, which means a formless system or a real one, as you can see. And you can see comparing the different aspects. Then we have also JWST from NB. She's working with the HST data with a sample of 16 targets. This is an example of dual systems, also with the system. Instead for water, I'm working with the new instrument in FDLT, so for near infrared regime. Here we have a 0 with the Gaia. And here we have, for example, here is the system, as you can see, the two HLI lines are very different. So we are sure this is a real one. And you can show we can detect the mass, of course. And instead, you can see is the two lenses that are normalized, okay? This is the lens system. There are some differences, but as I was saying yesterday, you have to take into account also macro lenses. So this small difference can be calculated. Then we have also in the different data from Erika. These are a sample from JWST of a lens and of a dual. And this is a very nice one, which you can see we are very sure because the two emission lines are nice, right? This is a painter shifted to each other. So it's a very nice object on Ching. And also JWST, we have collaborators observed 16 quasars, 3. And what they found, surprisingly, is that they found 5 multiple systems in this type of GN of a GN that were not set with one. They found compared with strong GN emissions, separation a bit large with respect to GNB, so up to kiloparsec. This looks a very high load function. We expect a load function up to 10%. So they found something which is in between 20 and 30. Of course, this is not a really statistical significant, and we really need more data to compare these results. What's next? Well, non-confirmed, we need to multivariate follow-up to characterize this difference. So, what is going on? Well, we have a proposal accepted Becama. So, with which we can study the gas mass and the polymer gas mass, because in this way we can have both the gas mass and the vector mass. and characterize these systems. Then we have radio data with EIA and LOCA. In the case of LOCA, we can also try to select systems with in this band. Then we have channel data from Israel and LBT in something like HNK band, which can also be some. With LBT, we are also trying to select systems, but this is our ongoing work. And how does this plot after going to work? Well, this is it. As you can see, the red circles are the GMP dual agents, and as you can see, we are really populating this range of this diagram. This is the separation versus the redshift. We are really seeing objects. We expect these are in the same galaxy. Of course, we should see objects compared that they are in the same galaxy. But this is very nice, and there is still a lot of work ongoing. But what's next? Well, we want to derive these quantities and the dual function, very important, which is nothing here because we want to derive the fraction of dualism compared to the total relation. So dual plus single. However, this is a lot of problems because of the sample selection. As before, we have selected only the original system. So it's not easy to derive this and also to compare to models, because the point is that we need a model with same resolution, enough volume for statistics, and the same sample selection. So we are working on these are very preliminary results, and still working on results. So we are still collecting data from both PLD and so on. So this is my last slide, and thank you for your attention. And I leave you with my first movie, which is an Italian movie, which title is Metro, which talks about a group of researchers, which after being upset about research and report, they decided to quit research and to start producing drugs. This is very fun. And this means Memoria investigata su investigadores on stage. In English is not so fun, sorry. Okay, thank you. Thanks. Please.
Thank you very much for a very nice talk. So I just wondered, do you know, in over your 20 days, what's the fraction of flows are dense quasars, and how many of them are in the stars with absolute position in this fraction?
Okay, the fraction of stars really changed if you compare before the most modern technique and after, because I can show you. No. Okay, here. This is a model that is not public because we are still working on it. We are trying to fit the analytical spectrum to find the stellar feature. And of course, the one here is the analytical spectrum. We are looking at because the first point you can go also because okay, you see the also the redshift also and in this way you are able to see there are strong limitations of stars. However, it's not 1% true because if the AGN is very rapid and the star is not, you see no stellar feature in the actual spectrum, and so something like 20-30%. Depends also on the luminosity of the AGN, so probably change also if you take amount of the data that is superconducted, it also depends. And another thing, if we set for the lens and refraction, it strongly depends, but it's something we are working on. Seems to strongly depends on the luminosity of the system, because with luminosity we are, because of observational reasons, we are observing the most luminous object, because we have a measure in the J magnitude of the system, So with users or rules, it lies instruments, and apparently there are more lenses less, but still the ones that we are talking about 12 systems, more or less, so we have a lot of work on it. So I don't have a fraction, but it seems so.
Can I ask a follow-up question?
Yes, please.
So let's play since you have like so like hybrid data. Like, did you see any like overall galaxy in those lens on?
Sometimes yes. We have some valuable systems, more with rules than declares, which is not problem. Some of them we also follow up with needs, which is the control speaker is the values and needs is the logic. In some cases, we are able to detect the galaxy which work. There is another work is on the formation of the study the properties of the galaxy or the system. So with the study and so on. Let's stand speaker again.
Next.
Hello everyone. I'm Ching Chen, and I'm a postdoc fellow at Johns Hopkins. And today I'm going to tell you about my research projects on kiloparsec scale quasars. So how we discover them with Gaia, and how we study their whole-scale property with JWST as JWST. And this is a large collaboration with many people across the United States, and it's also my honor to be here. So first, I would like to start with the scientific questions. Why do we care about the kiloparsec scale quasars? So Maria has already, I believe Maria has convinced you binary dual quasars are interesting. So let me emphasize this again. So if we look at the evolutionary track of the dual quasars, they spend lots of the time in this dynamical friction dominant regime, which is around kiloparsec, like 100 parsec to 10 kiloparsec scale. So in this scale, the dual quasars, they are like reducing their angular momentum to the dynamical friction in the galaxies. And after that, when they enter the parsec scale region, which is here, they become the bound binaries. So they reduce their angular momentum to like the three-body interaction with the stars in the host galaxy. And then when you enter like the parsec scale, sub-parsec scale, you run out of the stars in their host galaxy, which is so-called the final parsec problem. So you are kind of like stalled in these regions, but some theories suggest that if you have a gas-rich galaxy, it can help the binary to shrink their orbit and to enter the milliparsec scale, which they will emit like a gravitational wave in this region. So understanding like the population of the dual quasars from kiloparsec scale down to sub-parsec scale is very important to understand the binary supermassive black hole evolutions, and also help us to estimate like what's the expected gravitational wave signal from our current or future facility like pulsar linear array or LISA. On the other hand, we can also study their host galaxy property to constrain the cosmological simulations. So here is a very famous Hopkins merger-driven like galaxy evolution model. So as you can see, after the galaxy merge, their central supermassive black hole will also sink into a merging galaxy, and the star formation rate and the quasar luminosity will enhance simultaneously in this process, and there will be a quasar blowout phase after that. So our question will be, how does the dual quasars or the kiloparsec dual quasars fit in this evolutionary track? And can we test using our dual quasar sample with the cosmological simulation? So there are, thanks to like the large sky survey like SDSS longitudinal sky survey, there are lots of local kiloparsec scale dual quasars which they can be used to study the star formation rate and quasar luminosity as function of the separation or their merger stage. So as you can see in these figures, this on the left hand side, the right is like largest separation, and on the left is like smaller separation. So as you enter like the smaller separations, the quasar luminosity and the star formation rate both enhance below like 10 kiloparsec scale for those local kiloparsec scale dual quasars and redshift below 0.1. Also, if you use like other method from the morphology, and you can see the quasar luminosity and the star formation rate also enhance when you go to like later stage merger, which is the C and D here. However, we want to know like how about like the cosmic nuke, which is at redshift 2, where the star formation rate peaks and the quasar luminosity also peak. So this is the redshift regime where both quasars and mergers are like more violent. However, there is a problem when we go to higher redshift from a local universe. As you can see, this is a collection of all the confirmed dual quasars from the literature. And the y-axis is the projected separation, and the x-axis is the redshift. So as you can see, like at low redshift, like redshift 0.1 each, we have hundreds of dual quasar or dual AGN down to maybe sub-kiloparsec scale. So we can do like lots of statistical study for this, like from like 1000 kiloparsec down to 1 kiloparsec. However, when you go to like higher redshift, let's say redshift 2, the angular diameter distance increases significantly. So for the typical like 1 arcsecond, if you work on like optical astronomy, you know like this is the typical angular resolution of the ground-based telescope. So you can only resolve the dual quasars around like maybe 10 kiloparsec scale. So we need something else, some space telescope or some new technique to discover this unexplored region in order to study the statistics of dual quasars at higher redshift. So I believe you already know about Gaia, but I still want to like talk about this again. So Gaia is an all-sky optical imaging survey. So you will imaging the whole sky with very precise astrometry. And it can be observed more than 1.3 billion sources with a very deep like optical magnitude down to like G equal to 21. So it has an excellent resolving power, which can go down to like 0.5 arcsecond. So it can resolve most of the quasar pairs or dual quasars down to 0.5 arcsecond, which correspond to like 4 kiloparsec scale at redshift more than 0.5. However, the most important things about Gaia is its excellent astrometry, which is like 100 times better than its angular resolution. So it can help us to discover the unresolved dual quasars at even smaller scale. So here I would like to introduce our new method, which is astrometry. This is kind of like complementary method to the multi-peak methods, which we want to discover the dual quasars, which is unresolved in Gaia, but they can discover from the astrometry jitters. So the principle of astrometry is like this. So suppose you have two supermassive black holes, and they are equally bright, but they are unresolved. So what you see is just a blended sources. But if you measure the centrally, it will lie in the middle of two quasars. But if one quasar is brighter, so the central will shift toward the brighter, and vice versa. So because we all know quasars has its own intrinsic variability, and for the dual quasars, there will be like non-coherent emissions. Because Gaia scan all sky hundreds times. So you will have a central measurement for hundreds times over 10 years. For the current data release is 5 years. So in Gaia, we can use this technique to detect those unresolved dual quasars by measuring the astrometry jitters in those sources. So we can discover even smaller scale dual quasars. So here is our kiloparsec scale dual quasars candidates. So if you remember from Maria's talk, after we discover those candidates, we still need to do follow-up observation to remove the contamination dense quasars or some superpositions. So as you can see, with those techniques, we can populate these unexplored regions down to 1 kiloparsec scale. So which will help us to understand in this galactic scale how does the dual quasar interact with their host galaxies. And here I would like to talk about one of the confirmed 3.8 kiloparsec dual quasar at redshift 2, which we have the new JWST IF observation. So here is just to show you how this confirmed dual quasar look like. We use multi-wavelength observation in order to confirm this one is now a lens quasar and it's now a star quasar superposition. So here I would like to introduce you our new JWST observation. So we have the JWST near spec, which is the near infrared IFU observation, and also the near mid infrared observation for these targets. And as you can see, so it can fit in the IFU cube. So we can use the near spec IFU, for example, the H alpha and H beta to study their ionized gas in the host galaxy and also obtain their star formation rate. And also in the mid-infrared IFU, we are lucky to have the Paul emission 3.3 micron. So we can use this Paul emission to get another independent star formation rate estimate for our dual quasars. But there is one problem with the quasar because the central quasar is so bright, so we need to subtract out those two quasars. So I will not talk about this technique here, but if you are interested in how we subtract the PSF out in the IFU cube, I need to talk about this. And so using the quasar subtracted a narrow H alpha line, we see a very interesting morphology of the H alpha centric velocity map. So we see there is a giant gravitational disk around the dual quasar, which is perpendicular to the two quasars. It's kind of surprising to us because usually we think dual quasar reside in the merger, so there will be more disturbed morphology. But instead, we see this very nice rotational disk with velocity of 200. So this is it possible is like those two quasars, they are synchronized growth in one host galaxy, or there are like different other theory will involve instead of the merger-driven scenario. But it's only one target, so we still want to have more targets to test if all the dual quasars they are mergers or they are in this kind of like single galaxy kind of morphology. And how about like in the mid-infrared? So we have the Hall emissions. So from the previous talk yesterday, we all know like Hall emission is kind of a good star formation rate estimate. Although like there are like some like other bias you need to consider. But for our targets, we detect like the Hall emission 3.3 micron, which we use it to estimate what's the star formation rate of our targets. And we find out like the star formation rate of our target is 1,000 solar mass per year, which is very high, like 5 times higher than the mean of the infrared for quasar aggression 2. And we also have the ALMA observation of CO, so we can estimate what's the molecular gas abundance of our dual quasars. And if we compare the star formation rate of our dual quasars versus the molecular gas mass, we found like for this dual quasars, it lies above like hundreds times above like the typical Penny-Hashimoto level, which suggests like like the molecular gas might be depleted, or due to like maybe longer elevated like stage of star formation, which might suggest there might be like some enhance in the star formation rate and the quasar activity in those dual quasars. But again, we still want to have more observation for more like confirmed dual quasars instead to test this theory. So I will leave you with those takeaways. And before the questions, because I'm from Taiwan, so I would like to introduce you this movie, which is called Cap number 7. This is a 2008 Taiwanese romantic musical film. It was like the highest grossing like Taiwanese romantic film. The reason I choose this film is because when I came here, so this film was like filmed in a small coastal town in Taiwan. So the weather is very similar to here. So when I came here, it kind of like remind me of like the weather and the culture there. So if you want to see, just let me know. All right, thank you.
Okay, this is probably from you and also for Maria Vittoria. Do you have an estimate of the coalescence time of the best candidates and then of the merger rate, so prediction for the future yields and other gravitational observatories? I mean, from your work, can you go on that or?
Yes.
Okay.
Yeah, so I think I guess you're asking like, can we use this like quasar sample to estimate like somehow maybe to like a semi-analytical model, and what's the calculation of the binary experimental like in Sub-Arcsecond scale, and can we use that to ask like expected like ETS or something like that?
Yeah, something like that.
Yeah, I think like right now we are still in a very early stage of like identify those like dual quasars. So if you remember like we need to spend, because there are so many scattered and there are lots of like lens quasars combinations. In order to like get rid of like those lens quasars, you need to like do lots of follow-up observation in order to like have a confirmed combination of the dual quasars. But I believe like we can still also use like more like larger like scale, let's say maybe more than 10 kiloparsec scale quasars, and then use them to somehow estimate. But that's a good question. It's also like one of like my like future plan to do like those calculation study to infer this.
Okay, so I'm very myself. I was curious about this image showed the kinematics of this cloud JWST data. And so it looks like you can identify which ones in the center of this, or both are in the center. I mean, they have exactly the same direction.
Right, yeah. So they're so yeah, like both quasars have a similar direction.
Okay.
And yes.
And the clouds are more similar to one direction, or you're not saying?
Yeah, I think like the cloud sorry, what's your
So I think, can you identify if this gas is connected to one of the places, or you don't
yeah.
Right. Yeah.
So I think so both quasars are very similar direction. So the velocity, like offset is only less than maybe 100, no, like 50 kilometers per second.
Oh.
So they are very similar direction, and yeah, so it's very hard to distinguish like is it from the one of
yeah, maybe the cloud is connected to both.
Yeah.
Thank you.
Thank you, Javier. Very nice. I wonder, since Gaia is limited by the optical band, so there is a strong bias in obscuring what we can. I'm wondering if there is a facility, or will be a facility able to do astrometry also in the area environment.
Yes. I think like Maria mentioned like Euclid, and I think in the future we also have Roman space, so it will have like some high cadence. Although it's like now it's got in some part of the sky, we will have like high cadence surveys which will provide a lighter for all the targets in the region. So we can also do like clusters, stare lighters. Yeah, even because like Roman is also really good distance.
Thank you. Okay. We don't have time to very quickly.
Understand the velocity here. Your right hand down is plus or minus 250. If you look at the left, it's like plus minus 400.
Right. So I think because it's corrected for like the inclination angle, something like that.
It should be bigger.
Right, so it will be bigger. Right.
Yeah, 250 makes no sense because the black hole is 10 to the 9, right? So it's like 87. 250 is like the looking.
Right.
So that's just how the outcome.
Yeah, I think like like velocity is a little bit bigger than like the Milky Way. Yeah, but yeah, you can talk about it.
Yes. I think this our next speaker is Vittoria, Paola Severgnini.
Good morning, everyone. I'm Paola Severgnini. First of all, I would like to thank the organizer for this wonderful meeting. I'm very happy to be here. Today, I will talk about teaching environments. So I will refer to pairs of Indiana that are separated by parsec or sub-parsec relative distances. So the numerator will go towards the center parsec region. Okay, and I put in this slide one of the main conclusions of my talk, that is that the observational test of the environments is not only complex, but is still a completely open challenge. Okay, first of all, let's use our team, or at least the core of our team, and the red names are gamma switches. In the previous talk, we discussed about dual HDN, so HDN are kiloparsec relative separations. But in the last stage of the dual AGN phase, the two black holes are hosted by the same galaxy. And right toward the center of the same galaxy may be through dynamical friction with galaxy sign but they reach relative separation of parsec or sub-parsec. In this stage, the system is called binary. The two become gravitational bound to each other and start to emit gravitational waves in the low frequency regime from the CX down to downwards, depending on the mass of the system. And just a comment for the Andrea question, it is to a stage project can also stay for GWST. Okay, so the two black holes can also make quasars for the new and more massive black hole. So why is it important to study binary AGN? Since together with dual AGN, they are fundamental to understand the formation and evolution of the group. And in particular, they are important to understand the role of merger on the cold group and also on the activation of the group, so on the AGN. And from the gravitational wave side, these tools are fundamental since they are among the most powerful emitters of gravitational wave in the low frequency regime. So, as already said by Ronnie, they are crucial for current and future gravitational wave, So, how we can search for them in electromagnetic events, how we can catch them. For a relatively wide binary, so separated by parsec scale, it's possible to directly resolve this system through, at least in the local universe, through very high angular resolution, typical radio observation. And here I report the dedicated image of the only binary AGN confirmed so far. So it is this double factor radio cores with the two cores separated by more or less 7 parsec. Okay, it's by the collaboration, the collaborator of 2006. But for radio required closed system, okay, it's very difficult to directly image this system. And so to catch directly and resolve the binary AGN, and so we have to rely on indirect based mainly on the spectroscopic identification or photometric environment. So before to present some of the main electromagnetic traces, I show here one possible physical configuration of a binary AGN. So we have the two manual black hole, and we refer to massive black holes, so with masses larger than 10 to the 6 solar masses, and nearly equal masses. Each of which has its own medium accretion disk that is accreting material from outer circumbinary disk. And the mini disk and the circumbinary disk are the main responsible for UV optical continuum emission in the environment. Just above the two black hole, there are cones that are responsible for X-ray emission, and at some parsec distances from the two black hole, there are broadline region that produce broad, strong emission line in the optical and UV. So as you can see from this schematic view, this binary has the two broadline regions that are still separated. So the two black holes are at distances that are larger than few tenths of parsec. And we call the system like loose binaries. Okay, in contrast to the closed binary that have mid-parsec relative separation. Okay, for this binary, one of the ways to catch them in the electromagnetic is usually to search for double-gated or asymmetric broad emission line in single eco-optical spectra of AGN. Okay, the idea is that if each of the two black holes can its own then we can see the blue shifted and red shifted emission line produced during motion. Okay, so the problem is that this feature, this specific feature, are not usually associated with the presence of binary gem. It could be produced also by a chance superposition of different sources and different ratios. Could be due to harmful object, but again, could be produced by a symmetric distribution of a single variation around a single region. Like in the case of PG 130.2, that are one of the most famous binary PGM candidate. This candidate shows indeed asymmetric broad dimensional line parameters. And Fabio Monti, as a part of our collaboration, has recently analyzed expressed data from this source. And the result is that the asymmetric H gamma and H beta, in this case, broad dimensional line, could be due mainly to a discovered geometry of a single program, most probably produced by cell. So, to be able to work out the presence of the single code that is mimicking the presence of binary PGM, the possibility is to perform a spectroscopic monitor longer than the orbital period of the putative binary PGM. Okay, and so in order to search for periodic variation variability in the line profile, energy, and intensity of the broad dimensional line. So in order to check if they are placed in the orbital motion of the PGM, like shown in this figure by proportion. Okay, the problem is that for loose PGM, we expect, for those binary PGM that are separated more than a few tens of parsecs, in which the two program regions are still separated or at least detachable, we expect periods that are more than 10 years long, up to 100 years. It's very difficult. It's not impossible to follow this source with monitoring. On the contrary, it is possible for close binary, for milliparsec separation binary, that to have period ranging from a few years and down to days. But for close binary, program region are already mentioned because they are milliparsec separation. So we have to use X-ray emission line. We have to use that closer to the core and allow us to follow the orbital motion of the two black holes down to very close relative separation. Okay, another tracer of the presence of the parsec binary PGM is the presence of periodic variability in the light curve of PGM. So periodic modulation are expected for different effectively the motion of the PGM, and so far hundreds of quantities has been found, mainly in the optical band, but also in the X-ray band. But unfortunately, most of them have been questioned so far because it's very difficult to distinguish real periodicity from the stochastic variability associated with a single AGM, the so-called red noise. In order to distinguish non-red noise and real variability, the real periodicity, very long-term lecture are needed, able to sample more than 5 periods. So I report here one of the most common binary PGM found so far to calculated variability, that is J287. And for this value, there is a line curve in the optical band that is more than 100 years long. So, in which that show periodicity flares about every about 12 years. And the idea is that there is a primary black hole and the secondary black hole that is orbiting around the primary one, intersecting the efficiency in the primary one every, let's say, 12 years. Okay, and another promising black hole Asian binaries is MGG plus 11 that has been found by our collaboration. This source is optically classified as a secret in the local universe, This is the HST image. And I show here the Swift X-ray director properties candidate. This director is long about 20 years. And as you can see, there is a possible periodicity on a time scale of about 25 months or about 2 years. If this periodicity is due to binary region, so this galaxy cost binary region with masses of about 10 to the 8 solar masses and a kiloparsec. Okay, this target was observed by Chandra recently. The data have been analyzed and published by foreign collaborators in 2009. The high angular resolution of Chandra allows the output to find the second source close to the main target. Okay, here is the HST image of the second source, the primary target and the second source. Okay, but I would like to stress that the second source of an X-ray that is about 100 times 10 with respect to the main. So the second target will not be responsible for the X-ray variability. Again, for MGG plus 11, we have also X-ray spectra. They can be a different kind of our monitor. And these are XLP Swift spectra, but I go also the Chandra spectrum. And apart from the higher rest rate emission line, we tentatively detect also a second line, tentatively detected. And the interesting thing is that the energy of this possible second line is correlated with the flux state of the source. So when the source is in a high flux state, we see a possible blue shifted emission line. Why? When the source is in a low state, we see a possible red shifted emission line. Okay. So we find observation to confirm it is a result. And if a binary region is present, so the mass is the masses, the separation is of order of milliparsec, while the sense time is of order 10 to 4 years, so 4 years. And this is a typical minor region that emits gravitational wave in a non-frequency region. So it is supposed to be detectable by the and unfortunately the gravitational wave state for the source is a factor of 10 failure of the PTA current limits. So we cannot resolve it at least now, but in the future. Okay, so I stop here. I will hear my conclusions, and in particular, I will hear my film suggestion. That is a big text. That is a Italian film ensemble with the Italian IP, and talk about the duality that already characterized the phase among the need of good and the desire to explore new person. Thank you for the attention. Questions?
If I may, I don't have to explain the results of. No, the results from the lines are very interesting and exciting. We are creating and the audience about the possibility to observe prism, this source.
Prism should be very important for this source. We are applying for time.
Maybe you want to explain to those who are not aware what prism is doing. What
you are not expert than me. Anyway, is an X-ray instrument able to perform observation with very high spectral resolution. So it should be very useful for us to have prism observation in order to be able to resolve the possible X-ray line. So the last thing should be to have case monitoring with the line in order to resolve and also to follow the possible emission. Thank you.
Paola, very nice. I have a question too with lines. So why the second line is always shifted?
It's always no, it's reshifted and is reshifted in the low states.
I want to ask about maybe you don't understand because you
it is less than 3 sigma. The significance is very low. Okay, yes, we need more data.
Why can't you use or different molecules and then
try to resist? And now there are public available metadata that we are analyzing. We are not surprised. And to wait that the data become public. But so just a comment. Even if we have only one short channel or example segregation, don't see, for example, the domination line. This doesn't discard the presence of the pattern, okay? And it doesn't discard the presence of the pattern high line in other orbital phases of the
I've been following some little lines and probably in the region, and usually variation is going, up and down, not really. So have you ever found a source that you could be sure that could be a double AGM? That could be a double AGM. I mean, because of the peaks coming closer and going away, because I only see variations of the now. So
apart from this,
you mean
in this case,
in the X-ray, but I mean,
maybe not. No, as far as I know, no, but Paola use some sources for which orbital line go monitoring from the blue side to the red side. Probably she is more informed than me. Do you have in mind some example?
No.
I don't have in mind any specific example.
Okay, it's where you took the You cannot hear you.
Can you hear me?
Yes.
When you can start selecting a sample which is classical typical file, and then I go to typical file of source of flotation rate. There is sort of obfuscated definitions that is repeated by more than 300 kilometers per second, typically around 1,000 kilometers per second items. To the blue or
It seems that is changing.
there is some application.
So can I ask on what time scale?
Before we talk about many data, I will talk about the static. Because in this way we can select and check. The point is that there is a location of the gene sequence. The sequence in which you have a high probability of finding the identification profile. That is a good starting point to consider a peculiar profile which may be with the ongoing over several years turn out to be candidate.
So it's very good.
So I wonder if you search for like other signature, for example, like meaning this is the top of the circuit, like this, and there's like some gap, which some people suggest like there will be like galaxy, CE, like X-ray and maybe something like that.
For this feature, but I know there are some output that are searching for this feature in the software and hardware.
Yeah, I was just wondering if this can be done with this.
It's then the speaker is Erika Benítez. Thank you. I'm happy to be here and to be able to share our project that we have doing some years ago. I'm going to speak about our project with the different spectroscopy with the dual candidates and in the research. Thanks to my previous speakers, review the dual AGN software in a very extended way. But let me show you this fantastic diagram that was published by Chen in 2023. The dual AGN are formed with we think they are the result of minor galaxy mergers, although there are recent results that is not always the case. But in this practical scenario of cosmological evolution, we can think about the galaxies when they are going closer to the dynamic accretion phase. We define this one AGN as two active objects, accreting objects that they are very luminous. The luminosity and the star formation is going even higher when they get close. So this is the dual phase. In the literature, you can find several definitions. People think that they can be specified as dual when the radial separations in the sky are less than 30 kiloparsecs. More recent simulation results point that the better shows for defining is whereas radial sky separation less than 10 kiloparsecs. When they get closer, they can share to the same galaxies, but we can have these cases, and when we have one AGN pair, then we only see one galaxy and the other we do not see. We see an active massive black hole, and this can be connected, for example, the symmetry profiles that the previous show us, mainly that will be a consequence of this kind of stage. And there are also defining the offset AGNs that we have both in different galaxies. So there here, I just wrote some statistics, 80% of them are right, those dual RBNs, and they will merge in about 500 megayears. And there is an hypothesis that they suggest that offset AGNs are formed predominantly minor mergers. And there is, as I said, one only AGN active. Dual AGNs are becoming very interesting because they are difficult to identify, but they are the precursor of the most iconic gravitational waves event in the universe. So they are becoming very interesting objects to look for in the nearby universe and the far universe, and the Gaia universe also. For instance, the important phase is the Ibarra phase, when they are bound, gravitationally bound objects after the dynamic accretion phase. Okay. So there are several techniques to go for them, variability, as you saw in the previous talk. There is also the parsometry technique that is JWST applied in Gaia that's very interesting and it's very useful for higher residuals.
But the beginning of the story in our group is related with the identification of double peak narrow vision lines in the optical spectra. And remember, it started with the Sloan database 10 years ago, more or less. And the idea was to visually identify galaxy pairs and identify those with double peak vision lines. So, like this example. So, we started to study these objects, looking for them in the Sloan database. And then, in that epoch, a lot of catalogs were produced with several double peak AGS candidates. Now we know that this is not the best way to look for them because the kinematics can mimic a dual object. So it is not, and also the optical band is not the best band to look for them. But this is we have found that it's a good starting point to study what's going on with these candidates discovered. So it helps to look size. So this is an interesting figure that mimic these two close black holes, and why we find these double peak narrow vision lines because they are close enough. An active pair of supermassive black holes can be found in a galaxy merger, but also in galaxies that do not show evidence of merger. That's also important. This is the farthest close found in the literature, as far as I know. Okay, another important point is besides the kinematics and the spectroscopy feature that we look for them, we also find the necessity to study them in multi-wavelength bands. Multi-wavelength bands are crucial to truly identify as dual AGNs because they can be obscured in the optical bands, so we should go to the radio or to the X-ray band, as we know is the perfect bands to look for them. So here I have a diagram. It's a recent paper by Ruminor that in a single unperturbed galaxy with no signs of merging shows in the radio bands a double nuclei of the object. Also in the X-ray bands, well, this is the first object discovered as a dual in the X-rays. This is a very famous galaxy discovered by Formosa in 1640 in the X-ray. So X-rays are very useful to identify them, and also in the infrared now we call the James Webb telescope, and we can do a little work with especially high-redshift objects. I'm really confused with this. Okay. So this is our project is HT characterized dual AGN. What you see Zihuagn and MEGARA, an instrument located in the Gran Telescope Canary. This is an instrument that was developed to work in the MOSO and the IFQ mode. So we started our observations a few years ago with this setup. We started, as I told you, looking for galaxies that both nuclei can be well observed inside the field of view of MEGARA. And up to now, we have a collection of 12 galaxies observed with different PTH. This is related with the redshift of the objects. And the majority were observed using PTH that can cover the blue and the red part. Although in some cases, we got only data from one, maybe the red part. And we are still working and still asking for time to complete another sample that we have. Up to now, we got 18 hours, near 19 hours of observing time for our study with GTC. Okay, so let me show you our work. The first work we published is about a candidate, a triple agent that was known as a triple agent candidate in this source discovered in the Sloan, was in the Sloan database. So we decided to observe this with MEGARA, and then, as I told you, the field of view of MEGARA inside this red box. So inside the red box, we choose 5 different regions, 1, 2, 3, 4, 5. And in order to see the kinematics at kiloparsec scales associated with this object. So these are the spectra after the revolution process, the spectra we analyzed. For region 1, we see that this region 1 shows at least in this part, the village beta and the village alpha, the double peak red blue emission lines that were needed to use to fit their profile. The object number 2 is a single object without double peak emission lines, and the object 3 it also requires the inclusion of double peak Gaussian emission lines to fit. Regions 4 and 5 they were discovered as a single peak because they are in reality star-forming peaks. So the kinematics that we found in this object very interesting. This is object 2. So object 2 we found it is approaching us at minus 500 kilometers per second to object 1. And we also have the possibility to do the astrometry and to estimate the separations between object 1 to object 2. And then, so object 2 is here and object 3 is in the lower part. So object 3 is approaching us. That is a result of the cinematic results of the MEGARA. And okay, also we need, in order to establish the nature of the sources, we worked the one diagram because we couldn't build the BPT diagnostic diagrams. We don't have the group part with enough cyanide to know, so we have to study this only in the red part. And we find that, as I told you before, the regions 4 and 5 are associated with star-forming regions. Region 2 is associated with strong AGN. Region 3 with a weak AGN, and we found that the central object that is low is classified as the AGN is a fake AGN. Also, in the right side, you see the X-ray study. We downloaded the archival data source, and we found that precisely in region 1 there are no X-ray counts, so there is no possible association with an AGN for an object in this region. Also, we work with the Hubble Space Telescope archival data. So we downloaded this data with several filters. Remember, it's the infrared and the UV map. And we found that the objects here, the object 2 is very disrupted. Here you can see because of the merger. This will be the low AGN galaxy, and this is also a very open arm galaxy associated that is approaching towards pair 2. So again, what we found was that this system is not a triple AGN, instead it's a dual AGN characterized by a Cipher 2, that is object 2, Cipher 2 galaxy, and a Liger 2 that is interacting with the object 2 and is producing these collisional star-forming regions that we found in these images. That should be the result of the collision between these galaxies as predicted in some simulations to be the case. Okay, that was a very interesting object and shows the ability of MEGARA to resolve the kinematics at kiloparsec and disentangle the nature of the nuclei. So keep going, and now we are going to present the results of work that we are doing now in progress. This is an object that is very well studied with ALMA, for example. It's a merger, and it looks like in the slow images, it has two nuclei associated. But the point is that in a previous study done with the LBT telescope, published recently, this work with long-slit LBT data found that these two galaxies that have a separation of 5.1 kiloparsecs shows two narrow components, and the aperture they use for the spectra is 1.7 kiloparsecs, and they found that if you, well, I don't think you read this, but if the red triangle and the red square belongs to this object, and it is found that one of the objects is in the region of the Seifert, and the other one is in the region of the composite. So sometimes the DPT diagrams can not tell us the nature, and we need to use another kind of diagrams to disentangle the nature of the nuclei. So this object, we are again now with the HST data, and this is a red image, composed image. And in this case, to study our data with MEGARA that we published in 2023, we selected these three different regions, like A, B, and C, in order to study them separately. This is our this is the spectra, and the profile fitting again shows that looking this in a zoom version, that we need two lines for the narrow line, the regions, and in addition we have a third component. So we have blue, red, and a third component associated what we have shown here as in green as C region. See? Okay. What is interesting in this analysis is that the full width and half maximum of regions A and B shows the same full width and half maximum regions. Okay. But the C component has a broader component, but it is attached to AGN. Okay. So here are the BPTs. In this case, we can observe in the BPT diagram that again we have, as in the previous work I showed you in BPT, that the object C it is located in the locus of the composite objects. So the right, the one, and the left diagrams. Here there are equivalent diagrams that show that the regions A and B has no hints of agents, and also the fullness of the maximum as I showed you before, but they do show a strong component for the AGN. Okay? These are the velocity maps. Again, in regions A and B, so we have here the paths. This is for oxygen-3 and H alpha, they are very similar. So what we have with MEGARA is an excellent resolution, spectral resolution. This is our 1 sigma errors in these diagrams. But we found that the only component that shows hints of rotations is component C. So some results. MEGARA shows that the high spectral resolution allows to confirm candidates, study the kinematics, and in the example that I showed you just now is that they cannot be associated with a dual AGN. So we can see that in the optical region, at least we have three similar different components, and we can talk about a dual AGN associated with this merger. And I show you evidence supporting that this is a dual AGN and not a triple AGN. And we think we are going to keep going with our sample, and that's all. Thank you. Questions?
Thank you for the talk. My question is, are you planning to use the NGBLA for these subjects to resolve
NGBLA? Of course, the area map is irregular. Yes, of course, one area map to support evidence for what agent is the rate parameter to have the higher resolution. And the new generation data will be an excellent telescope for looking for them. Also, there is a project that is X-ray that is always in it's on development. Also, on X-rays, there are facilities designed especially to look for tools looking for hard X-ray vision.
Yeah. I was just wondering, why you say that your one object, number one, was not an ADA field? You have with some of the other one, which we said is a strong ADA.
Yes.
Might have very strong ADA.
I'm going to say anything. I can tell you. We find object one is in reality a entire galaxy. It has no activity related to the gene and no with the star formation. It's very interesting. And the other ones, the object two is the Zebra 2 is contaminating with the extended emission, and it's this emission extended applies object one. So object one, that's the emission appears with the double peak emission line. And the object, the northern object that is object two, it is a liner 2 and also has a contamination with the extended emission of object one. So this is a real double peak emission galaxy that is connected to the GM. So it's very interesting that that's the thing that we can do in MEGARA. Okay, it's time for speaker.
One more question? No, okay, sorry. Could you please go back to the slide with the spectrum that you showed recently? The spectrum, where you showed no raw components, instead of no raw components.
Oh, sorry. I forget about that. Sorry, but this is relevant. Jacopo, this is for you. This is you asked me for a company research, so this is a version of free teachers. Not drunk people, they're thirsty. Okay. This is for you. And since we have anchors to date, I remember this beautiful picture with the travel spaces 30 years ago. Movie what I recommended is very okay. Now I'm going to this mask. This one?
More back here.
Okay.
Yes. Could you explain again? I'm sorry, I did not follow. For where you say that you said there are no raw components for the Zebra 2, but that certainly looks to be a broader component in the spectrum. So I was curious if you could please explain again how you interpreted that. It has to do with the AWAGN.
Yes, of course. Well, this is the spectrum from Gaia. So for the narrow components, we used to fit them with the red, blue, and red components that we think are associated with A and B. And A and B, we found that they are schematically different components, but they do not show elements of AGN. The full widths are 110 kilometers per second. And then we have the component C, that the H alpha component C is much more broader, okay? Much more broader in the nitrogens and in H alpha itself.
Okay,
But not so much as to be
I understand, thank you.
okay, let's go here again.
Our next speaker is Hector Ibarra Medel.
Well, many thanks. Thank you everybody for staying here and for the invitation for the conference. I am also part of the collaboration is both by Erika Benítez, Erika Benítez, and Gaia, Erika Benítez, Javier, and Sodora, and we will present in this software by photography. But we have run, as Erika told, 30 targets, and this more or less 19 hours of sense of time of MEGARA EDC. And in this case, I will do the analysis because for the past presentation, I talked about what's important to the dual agents and the characteristics of the dual agents. In this case, we will focus on the Arcadian AGADG. This is interesting actually because if you can see that you have two nuclei. You have an extended also emission. You can see this blue part that is an emission of CNG, but also is previously classified as an active galaxy. In fact, you can see the spectra and also in 1983 classified this as a sacred 1.1. But more interesting is that it has also several observations. One for this one, other for manga, and the last one of MEGARA. This observation from 2014, 2018, and 2023. And we see that in the graph component has achieved it's very variable. This is an engineering that is good in the graph component change the time. And then this is a very interesting candidate to be a dual agent that present is very specific. An agent, one of the new positions agent is also have a variability in the graph component, and therefore we will explore this in MEGARA EDC. The MEGARA EDC has also it's a very nice acoustic program. And this is the example the galaxy. The field of view of MEGARA is located here. And we have worked with the galaxy between March 2021 and April 2021. In two spectral regions, one is in green and the other is in red, and not the H beta and H alpha is the emission lines. We have spectral resolution between 25 per second and 20 per second. And this is the field of view of MEGARA, this is the different one, and this one is the restricted image in the data. Optimally, is synthetic RGB image using the data from the iris spectroscopy. And we represent these fields using the JWST methodology. More interesting, we can also because it's adaptive, we can use the H values, and you can see, for example, between one using the H values. Okay? The other contribution is the spectral spectroscopy is that you can see different spectral regions, and you look like here you see the shape of this Taiwan with the graph component and the emission lines. And the second look like you also see a contribution of the second component. So there is a key difference that we need to take into account that the strong emission of the central loop can contaminate the aperture near this near the position of the most right part. Therefore, we have this that the contribution of the agent can obscure the near regions of the galaxy. And I don't know interesting also more interesting the physics of the cost. Therefore, the agents try to move quickly and to obscure all of the indicators that because can provide give this information. Therefore, this. And to do that, we develop a set of codes. This is an analysis tool that try to treat the spectral thinking. And the basic idea is really select, for example, the central region, and we try to model this region. And this is the central region of this case. And now we will focus on the Ibarra component here. Why? Because the Ibarra component is the only part of the spectrum that we clearly know that is came from nuclear radiation. It's only produced by nuclear radiation. And if we can fit this spectral region, this axonal structure, and obtain this distribution, especially resolved, we can trace the emission of the PSF of the quasar. And this is one, but obtained from MEGARA. You can see, for example, in the simulation, recently, you can model the PSF. And then if you can model the PSF, you can extract from the image the weighted by weighted and obtain the spectra free from the contribution of the aging or the central aging. For that, we also develop a set of codes. This is one we can screen the model in that's the idea is that you have the observation, you have the model, the basic model, you have the subtraction, and you can explore all of these that regularly will be considered by the contribution central aging. This is an example. You can also model on this PSF. This is an study that we are distributing in a patient student using a set of lens quasars in the JWST telescope. And we can also model this PSF using the complexity of the PSF of the James Webb, and also multiplying by the number of images. This is the work of Erika Benítez. And this is, for example, the one of the results. This is the model of the PSF, and this is the residuals. These are still work in progress because we have also some residuals in this part. We can explore the contribution of the galaxies and the density of the situations. Well, referring to the Macayan 883, we model this. We subtract the contribution of the AGN, and we obtain this spectrum free from this contribution. And this is one. This is the spectrum. Yeah, once we are subtracting the contribution of this entity. This is the spectrum we can also see this one, but we are more interested in this part. If we look for this, it is that the second component has a spectrum. If we can move the whole spectrum exchange, we can also see the spectrum here. For more interesting is that we are focused so in the emission lines and near to the second well, we see this conductive. And this is the spectrum once we are in the contribution of this. Okay, then we model this ODP using a whole component and obtain then the kinematics and emission lines of each component. It's hardware story. We said this one, we model the amplitudes, including the maximums, using this NTS code. This is all of this estimation for obtaining the best fitting. This is the reference. This is the kinematics of the new component. We see that this extends the normal sequentially. If we see this the red component, the kinematics is also it is in the red part. We can also be more clearly with any difference in the velocities of each of these components. And this is a structure that is around 300 kilometers per second. We're leading to focus to 200 to 300 kilometers per second. But this is extended in this way, not in the second place. If we, for example, in emission, this is the total flux of the two component, and this is the clear we can see. We see that the two component has a strong contribution of this value, and this here, this is the alpha, the alpha, or this alpha part, the two component of the alpha group. And this is the red component, as you see, there is it's not a strong group, the principal contribution of the component is doing this extended emission. You can basically use this also emission. And we can also obtain the errors. we apply unity diagrams, we see that all of this standard emission is part of a star formation area, not an engine. This is also for the company, this is still a star formation area, not an engine, and this is a tracer that past merger or merger in progress. And with this merger, there are performance perturbation impedance and close the star formation. But it's not producing, or the second copy, this is not an emission of the engine. Therefore, the conclusions. Importantly, this is not a valid again. Yes, it happens. A second nuclear, and this second nuclear is good American progress. The first nuclear is an engine, it's a very engine that is also a variation of the time to the second nuclear. Therefore, it will be a very nice thing that we could call what we that's all. And I would like to finish with my new recommendation. This is Gaia of 1960. It's a very nice movie. For me, for example, this is well, this movie tells a story about a person is starving, and then he tried to hide with a turkey, and then he finds the dead. And he befriends the dead and tries to keep the dead, and then he shares his turkey with him. And this is the story instead. It's a very nice story to see in Days and Days of Mexico.
They can take us 8 minutes for questions. So, you're free.
Just for curiosity, maybe you mentioned why are some of your spectra missing wavelength range in the middle?
Yes, because we also put into the spectral ranges for the spectral range of MEGARA. You can select, for example, the spectral range in DKPH. DKPH is not covered the whole spectral range, you need to select and see. And the Ibarra is not covered because we don't observe this here.
So there are two spectra for
yes, the observations, the spectra, and then combined chips.
Very nice observations, and I wonder if these double bookings that you see in the narrow also would be helpful, so we could see the non part of going away back. So,
yes, well, yes, it would be an geometrical interpretation. Except by the fact that we see this measure. This one, mechanism. This is the second dimension. Yes, it will be a the other part is functionally, I will expect to be in this direction. Not in this direction.
Another question?
So, just a question, I guess I didn't mention. How are you constraining the results of properties in ACPH, mass and so on?
Okay, this one you are slide. Okay. Well, the good question is we can apply a set of stellar population synthesis. We know that we extract all the contribution of the AGN, and then we apply this, for example, actually, we can use satellite, or with the face, or the other one, is for the stellar population synthesis. That is needed for our stellar fitting of set of templates of single stellar populations using a set of age and places.
something different properties for the different sources that you are found there, or
Yeah, sorry. Are you assuming that the analysis of the two sources there is the same kind of population or taking different?
No, this is not a stellar population, but in the stellar population synthesis, you don't assume a specific set of properties. You have a grid of age and grid of metallicities, and the code will determine the best linear combination of these libraries. And therefore, you can obtain a different combination of age and metallicities in one region and a combination of age and metallicities in another region.
most of the talks today emphasize emerging galaxies where both the nuclei are active. Fundamentally, you guys tell us you're interested in emerging black holes. So actually, I don't really care if it's active or not. I just don't know what is a black hole and what the mass might be. So when I look at this image, the first question is, what is the mass of the two galaxies? Either one of them or both of them have bulge. And you try to disentangle that. High resolution multi-band images and quantum tools you can do. And so actually to know if they both have black holes and one is active, maybe the other is not active, or maybe both are not. Those are also interesting questions. If you're interested in black holes, you don't necessarily need to focus on the activity.
Yes. Yes, this is a very interesting question. The one is that well, this is one part of a very we are also looking from fossil traces in these early populations into the second layer to see that this other layer was active not us. Also, to try to study, for example, the properties of the host. This is why we are being very important with this extraction completely of the emission of the AGN to see, for example, these are properties of it. So in this case, we show you another line related work that was Zanchettin. We are also doing this one with a set of facilities. Okay, yes, a set of exactly the same with the non-galaxies. We subtract the contribution of the AGN and obtain the applications. And in this case, also obtain a very similar present. When the galaxy is active, you see that most of the star formation is also above the mean space. But if you integrate all the star formation of the full galaxy, you recover, for example, the favor of the mean space. So this is for the full extension of the AGN. If you see only the nuclear in the center region, we see this boost in star formation. Correction is. And yes, the question is yes, we are also looking if the galaxy is active or not, but also this another we can try to subtract completely in a very qualitative way the contribution of the AGN in order to store this space. And related this with the active galaxy.
Questions? Let's stand our speaker again, please. Stand for talking. I don't know.
Ahí la define de Solima,
Sorry, we have 5 posters. Those are them. Tres, 3, 4. So let's take Jocelyn, please present yourself.
Hello, my name is Paola Severgnini. I'm studying in Institute of Astronomy in Syria. And I'm going to present my tests of my bachelor. And it's called neural networks and modern approach to distribution. It begins from H2 regions. And it is tall, and it's three different neural networks. The first one is convolutional network that is with fixed images with this one, BR16. The second network is neural, and it's a dense network, and it's with three different layers. It's for the spectra. And the third neural network is with CNN, that is another convolutional network. And it's with the spectra again, but only with some contains characteristics. And in the methods that I use is with resident 50, that is for fixed images, and the results are too positive, and I achieved 99% of accuracy. I used 3,000 images and that, and it classified almost every AGN and H2 regions correctly. And I used F1 score and ROC poor, AUC poor, and also convolutional matrix for the results. And if you want to have more information, thank you. Next poster. Oh, Jonathan Guerrero, please.
Hello. Hello everyone. My name is Jonathan Guerrero. I'm a student at Medel in Puebla, Mexico. And I'm going to talk about my PhD project that consists in the classification of lasers, in particular in the circuit. Well, you know, lasers are special AGN characterized by the activity-oriented errors over us, and that is the most important feature of these technologies, right? So, we collect all the sources of the most comprehensive catalog that is the 5 VCP cats, and we select all the circuits, and after this list that is seen to match and we got a final sample of 610 circuits. Now, we collect all the optical curves available, all the curves, in CTF of this sample, and we expect finite behavior in all the curves. But not all the sources behave as we expect. So you can see here, some sources has finite validity, you can see above, but another ones have characteristics like Hector process. There is a account behavior. So you can see in the table, and there are the results, and then the next is. Then, thank you. Then we collect all the image, value image possible for the sample in different services. And the service above most important, first lower VLDI. In order to check the kiloparsec process space, and when we suspect in all the sources that will be complex. Well, because with a laser, we expect a phone source in the radio image. And also, we explore the radio spectra in order to explore another means of the classification. And yes, we show that the Hector cube is often misleading, as many sources deviate from that spectrum. There is a lot of spectra that is still inverted. And also, we let for adopt the more accurate from the term DCQ, because, well, Hector cube is the same, and then the next one, on the next one. Confirm DCQ possible and now DCQ. And well, if you want to know more details, we that's it. Thank you very much.
Sí, ahora sí.
Now it's copyright time.
Pero la charla de 15 minutos. Pero dejaste de dar la charla de 15 minutos.